Okay, welcome everybody to the afternoon webinar session for today. Just a few short words up front. Today in the morning webinar session, we had some sound issues and also some video issues. It seems that the servers are pretty busy today. So if you have issues, you can type them in the chat. I can try to fix them, but most likely it's depending on the server connection of this webinar platform. And therefore you will receive a video of the webinar and you will also receive the presentation afterwards by mail. In case you did not receive the mails of the last webinars, please just let us know. Write us in the chat or write us an email at info@linseis.de. Regarding today's topic, the STA, if you want to know something or if you have questions, just type them into the chat. I will answer them after the presentation. Looks like the sound issues are not so bad anymore, because in the morning we really had some troubles, but now it looks quite good. The list of participants is already quite full, so again, please type questions into the chat. I will answer them afterwards, and you will receive a video and also the presentation afterwards. Okay, today's topic is the STA, which means simultaneous thermal analysis. So it's a combination of calorimeter DSC and thermogravimetric analysis TGA, and together it forms the so-called STA. Before we start, let me just introduce myself. For those who do not know me yet, my name is Sebastian Seibt. I am head of laboratory here at Linseis since 2013 now. I'm responsible for service measurements and system and device evaluation, trainings, and customer support. I'm also responsible for dilatometers, calorimeters, and thermographic analysis. So this is more or less my topic today. So if you are facing issues with one of these instruments, you can also contact me directly regarding these issues. If you do not know the company, let me just introduce you the company. Linseis was founded in 1956 by this guy, Dr. Maximilian Linseis, here in Selb, northeast of Bavaria, right in the middle of Germany. We have our main production facilities here in Germany. It's still the same place. And meanwhile, we have also subsidiaries in the US and also in China. In both locations, we have our own employees. We have a little test and service laboratory, and mainly we do maintenance and sales. From there. In all the other countries, it's more than 65 countries worldwide where we have distributors and traders who are representing us quite well. They can fix your issues, they know our instruments quite well, and they get trained every year, and they are really experienced. So in case you are not living in Europe, if you're not living in US or China, you can be sure there is a Linseis distributor right around the corner who is able to help you. If you do not reach anybody in your country, of course, you can also contact us directly. The Linseis business area, or the main business area, is the manufacturing of thermal analysis instruments, thermal conductivity instruments, and thermoelectric material testers. Besides that, of course, service measurements and test measurements, and sometimes we also do research projects with some universities. As I told you, we were founded by Dr. Maximilian Linseis, who unfortunately died in the 1990s. And now his son, Mr. Klaus Linseis, is our CEO, and he is leading the company together with his two sons, Florian Linseis and Dr. Vincent Linseis. So these three people on the pictures here below are the CEO and his two sons, so they are in the lead of Linseis at the moment. So it's a family-owned business, meanwhile in third generation, which is something more or less typical for German companies. The product range we are offering, as said, begins with calorimeters, so differential calorimetry, or shortly DSC, in various types and models. Then we have thermogravimetric analysis, also a lot of different instruments. And the combination of these two is the simultaneous thermal analysis STA, which we are talking about today. Besides that, we are also manufacturing dilatometers, which was the first thermal analysis instrument we did, and it's also one of our key fields. So thermal expansion, shrinkage, sintering, and so on. And then thermomechanical analysis, which is a special kind of dilatometry, where you can pull and push and do investigations of E modulus and sinusoidal forces and so on. Then we have the field of thermal conductivity and thermodiffusivity. We are doing this by laser flash technique and as well as heat flow meters, hot wire techniques, and most recent devices, the TIM tester, trans-interface material tester, is also a hot plate method. They are all for thermal conductivity. And in the last years, the most recent products are instruments for thermoelectric properties like Seebeck effect, electrical resistivity, all temperature dependent, of course, thin films, microchips, and computing parts. And we are also investigating them regarding their temperature stability and their behavior at different temperatures. And the most recent instruments is the Hall effect, belonging to the thermoelectrics. And as I said, a lot of thin film analysis. Besides that, we are doing special instruments, that means high pressure and high temperature devices. All what you can see here can be equipped with high temperature or ultra low temperature furnaces. And for the most of these devices, we also offer pressure instruments and pressure versions for sorption analysis and a reaction behavior under high pressure. This is something that Linseis does as the only company on the market who offers the complete range of thermal analysis. So we are more or less a little bit unique regarding our special instruments and customization. A lot of competitors do not want to or are not able to do all these customization that we offer, which is a little bit what Linseis differs from the others. Back to our today's topic. As I told you, today we are focused on the STA, so the simultaneous thermal analysis, which is a combination of a DSC and the thermobalance, so DSC and TGA. What you see here is a schematic drawing of a STA instrument, and as you can see, there's a kind of block in the case down here containing a balance unit. So this balance unit is more or less a compensational balance. You have a counterweight, you have a place where the measurement system is positioned. In the middle is a fixed angle, and then it can move. And on that side, right beyond the measurement system, or the point where the sample holder here is fixed, there's an electric magnet that controls the movement of this balance, and there are light beams or light sensors that check the position of the balance all the time. So if this bar here of the balance is moving due to a weight loss or weight change, these two light sensors see the movement, they see the direction of the movement and see that it's out of position, and this magnet immediately will bring the balance back to the zero position. And out of the voltage this magnet needs for bringing the balance bar into zero position, out of this voltage the weight change can be monitored quite precisely. As I told you, the measurements system, or the sensor, how we call it, is positioned at this point, so it's fixed with the balance bar at that point, and then it's a rod that goes into the furnace, so the hot zone, the reaction chamber up here. The blue thing here, or the blue bars here, symbolize the heaters. In between there is the sample, the sensor containing the sample and the reference, and of course there is the possibility to couple the whole thing with a gas analysis. EGA means evolved gas analysis, FTA or MS. So you can bring a gas flow from down here up to there and then transfer the gas out into a kind of MS, GCIR, GCMS, FTIR, whatever. If you do the same setup but without a DSC sensor, but just with a normal TG sensor, you have the TGA version. And if you skip the balance, so if there's no balance down here, then you have a classical DSC instrument. So you see the combination of both really is both techniques within one instrument. The typical curve, or the typical thing that STA does, is it measures weight change, and simultaneously it measures the DSC, the caloric signal of a sample. The orange or the red or orange curves here show you the mass change or the mass loss of a sample that was just decomposed. And it loses some water and volatiles here, and as you can see, there is an endothermic caloric signal. The green line is the caloric signal, so an endothermic peak at the same place where there's this mass loss. So you can see there's a mass loss, and at the same time you can see the direction of energy flow, and you can also integrate the peak area and get an idea how much energy is released. This is what a DSC can do. So it's the same piece of sample, and you can really measure both signals at the same time. Of course, this saves time. You do not need to do the experiments one by one. You can do them within one instrument at the same time. The evaluation is quite easy. You can directly see which peak belongs to what signal on the mass curve. You get some additional information. As in this example here, there are some effects on the DSC curve, like maybe phase transition, maybe melting, but there's no signal on the mass change. So that means you can see there's a difference between effects mass change together with caloric effect without mass change, or even mass change without caloric effect. For instance, if you lose just humidity, or if some water is stick to your sample and just evaporates, you will not see a big signal on the DSC. So as I said, it's cost effective and it saves a lot of space. The STA product range that we offer covers a complete temperature range from -196 centigrade up to 2400 centigrade. That means most common thermal analysis applications can be performed with our instruments. Of course, we cannot do everything within one instrument, so we have different types for different fields and different ranges. First of all, there's the STA-PT1000, and as the name indicates, it goes up to 1000 centigrades. You have an integrated furnace, small thermal mass, so slightly higher heating and cooling rates than with the other instruments with the bigger furnaces, but limited temperature range. And then we have the STA-PT1600, and again, it indicates that the maximum temperature is 1600 degrees, which is true for the standard furnace that you can see here. This is a SIC standard furnace up to 1600 degrees, but the STA-PT1600 model series can be equipped with a furnace up to 2400, also up to 2000, and also up to 1800. So the furnace is quite modular here. And this platform is the most modular platform where you can attach almost everything. So with the STA-PT1600, you can do quite a lot of applications. Besides that, there's the STA magnetic suspension version. So MSB stands for magnetic suspension balance. It means we have the same instrument, also again with an external furnace. However, there is no rod going into the sample chamber. There is an elevation part, so an elevated small sample holder that's held by a magnetic force from a magnet that's outside of the reaction and measurement chamber. In case you measure very corrosive substances or very reactive atmospheres, you can use the magnetic suspension balance. For TGA, it's pretty easy. If you want to use it as an STA, so DSC signal and TG signal, there is a possibility to get a DSC signal out of the magnetic suspension balance. However, I have to be honest, the resolution of the DSC signal over MSB, in contrast to the classical STA, is not so good. Besides that, we come to our specialty. We offer all these versions also in pressure options or with pressure options. So first of all, there's the STA HP3. It's a tabletop pressurized system up to 50 bar within this small furnace here. And then we can go up to much more pressure, like 100, 200, 300 bars, depending on the model, with the STA high pressure 1 and 2. They are quite huge with sophisticated gas control, vacuum control, and they can handle a lot of pressure at the same temperature range like the others can do. As I said, this is something unique that the other competitors do not offer. You have now seen the model range, and then there is a design issue. And the question of design I want to explain, because I'm often asked this, and we are often asked what's better. If you set up a thermal balance, in general, there are 3 different ways you can do that. First of all, you can do a horizontal setup, so the balance aside, and then it goes from the side into the furnace. You can do a vertical system with the balance on top, or a vertical system with the balance bottom side, and then a standing sample or a hanging sample. In the past, or like 20 years ago, we did a horizontal system, and a lot of competitors as well did. In the meantime, technique has changed, and the vertical design is now the dominant design on the market. So 90% of the thermal balances you will find are vertical design. A lot of them are like this one, balance on the bottom, system on top. Some of them are hanging systems, and both systems are what is mainly used at the moment. Linseis balances are always standing design, so balance cell on the bottom side, sample on the top side. We can offer to build a vertical hanging system. We have in range, but most of our systems are standing design. Why? Let me just explain the advantages and disadvantages here. The horizontal system at all has a very small buoyancy effect. That means if the atmosphere and the gas flow rate within the chamber changes, the position and the weight signal of the sample will not change dramatically, so it's independent of gas flow and density of atmosphere and so on. However, it's very complex to arrange the sample in the furnace, so you have to open it from the side. It's very risky, sample can fall out. It's not so easy to handle. The sensor exchange and measurement system exchange is not so easy. And you have to use a quite high purge gas because of convection. In a horizontal system, you always have convection. And this is more or less the reason why the horizontal design is not used anymore today. And also, if you have a thermal expansion of your sensors, and it will expand if it gets hot. If you have thermal expansion within a horizontal furnace, the weight signal is affected by that, and this is a disadvantage that was more or less eliminated by switching to a vertical design. If you have a hanging or standing design, it's not so much different. So the advantage of a hanging design is that your sample position is slightly more stable, like if it's standing. The disadvantage of a hanging design is that there is a certain risk if you have a gas flow from top to bottom, you could blow the sample out of the crucible if it's a fine powder or something. In a standing design, gas from the bottom side to the top side, the risk of blowing out your sample of the crucible is minimized. However, the construction is a little bit more complex and it's a little bit more, how do I say that? A little bit more sensitive to vibrations and environmental movements than a hanging device. However, this is the design that has the most advantages for us, and this is why we decided to use this one. Of course, there are some hardware options beside the furnace that can be exchanged. We offer sample robots, so you can do and perform automatic sample control and sample loading, sample unloading. So you can program your analyzers like you can see in the picture on the left side. You can place many, many samples on the sample robot, and then the system works autonomical. All of our balance systems are usually equipped with a vacuum flange, so you can apply vacuum, and allowing vacuum means also allowing in any kind of defined atmosphere, like inert gases or reaction atmosphere. Doing so, we can offer to use water vapor, so the water vapor generator is something that's available. Various gas dosing systems, especially the pressure balances, need automated gas control. It's very hard to do a precise gas control if you have pressurized sample, so it's better to use software to calculate the exact amount of gas flow, flow rate, and pressure control. So therefore, we have gas dosing systems. And of course, we can couple our systems to any kind of gas analysis. If you want to analyze the gas that's coming out of your instrument, we can offer to couple FTIR, MS, GCMS, and we are not depending on one brand. So we can offer any kind of brand. For instance, we did Edgeland couplings, Bruker couplings, Shimatsu couplings, and Thermo Fisher in the past. For MS, we mostly use Pfeiffer, which is a German brand, which is easy for us to access. But we are not limited in the brand here. So you can, if you already have a system, we can couple that. It's also a spot where we are quite flexible and not bound to one partner or to one brand of instrument. This is just an overview. The slide shows you the temperature range, the available furnace, and it shows you what kind of atmosphere you can use. As I said, from minus temperatures up to 2400 centigrades, it's not possible to do this within one system. You have to use different furnaces for different temperature range. For the ultra high temperature range, you need a graphite heater, which restricts your atmosphere. You can only use inert and reducing atmosphere in a graphite system. At the low temperature side, you have a type K sensor because all the other thermocouples will not give any signal anymore. This allows any kind of atmosphere, but limits your maximum temperature around 1000 centigrades. In the middle range, from room temperature to 1600 or 1750, we have resistance heaters out of SiC, MOSI, various metals or infrared heaters, offering almost every atmosphere. Reducing atmosphere here is not listed because these thermocouples type B and type S are made of platinum, and platinum is not working with reductive atmospheres. So it's a little bit depending on the thermocouple at the sample or of your sensor and the kind of heating element. And beside our classical furnace selection here, we have some special furnaces, like we have an infrared inductive heated furnace with a high frequency field that allows very high heating rates and cooling rates. And we have a water vapor, specially designed water vapor furnace. As I told you, we can offer a water vapor furnace for the range from RT to 1750. As I said, you will get the presentation, so you can have a look on the options of regarding the furnace by yourself later. Beside the furnace, we also can vary the sample holder and of course also the crucibles. As I told you in the beginning, the STA is a combination of TGA and DSC. That means it can work as a standalone DSC and it can also work as a standalone TGA, depending on the kind of sensor you use. Classical DSC sensors, we have two types. We have a DSC heat flux sensor and we have a DSC sensor for bigger volume. A classical thermal balance, like a TGA, usually can handle up to 5 gram or 5 milliliter sample. However, a DSC is designed for a sample holder that carries 2 crucibles, each one 0.12 milliliter volume, and usually you have an empty reference and a sample containing crucible. So your sample is limited to 0.12 milliliters volume then. For a couple of samples, like if it's very inhomogeneous, 0.12 milliliters is quite less, so people are asking for bigger volume. Therefore, we designed this double-sized crucible for up to 0.25 milliliters, which decreases accuracy of enthalpy, but allows you to use a little bit more volume, and we have the 3D DSC sensor. This special 3D sensor has a couple of thermocouples at the side, trying to monitor the complete volume of your crucible. While in the flat crucible here, with the standard crucible, this metal frame surrounds your sample and tries to transfer the complete energy flow to the sensor. The key issue is, if you do not get the complete heat amount that's released or consumed by the sample, because your thermocouple is not touching it or you cannot see it, you cannot sense it, because the sample is cold on top and hot at bottom or whatever, your enthalpy is not accurate anymore. That means this 3D sensor with a volume of up to 1 milliliter sample decreases the accuracy of enthalpy, but increases the volume you can measure drastically, and it's still a real DSC. As I told you, beside that, we of course offer TG only sensors. TG only sensors are, the biggest one is 12 milliliters we can offer. We have 3 or 5 milliliters crucibles. Because if you do TG only mode, you do only have 1 crucible and not 2. You do not need a reference site anymore. And of course, we have various TG DTA systems. So DTA, in contrast to DSC, just shows you at what temperature an effect takes place, but not how much energy is released or consumed. So DTA, which means differential thermal analysis, is worse than a DSC, but still gives you an idea about endothermic or exothermic effects and the temperature the effect is ongoing, while a DSC enables you to measure the real enthalpy and the amount of heat. So DTA is more or less the easy kind of DSC, less accurate and no enthalpy, but bigger volume. And all the crucibles you can see here, of course, can not only be made of ceramic like they are shown here, they can be made of metal like platinum, gold, graphite, sapphire, aluminum, whatever you need. So it depends a bit on the application. Your sample should not react with your crucible material, and therefore we have many, many types of materials available. And then there are special crucibles like this mesh size, where the gas shall flow through the sample or through the wall of the crucible. We have this hanging kind of instrument where you can hang a foil in there and then watch the thermal mass loss of this foil, and a lot of specialties like that. For most crucibles, we also, by the way, offer lids with holes that the gas can get out of that, or crucibles that are really tightly sealed, so lids without holes. Some of them can be crimped. Ceramic crucibles cannot be crimped. So it really depends on your applications. So you should know what you want to do and you want to see. Regarding the applications, I want to describe what's typically done with an STA, so really with the combined system. So one of the most used fields, of course, is the decomposition analysis and thermal stability of materials. So What's always of interest in any kind of DSC, and especially with the STA, is the oxidation and thermal stability of polymers, or oxidation behavior of anything that can burn, like lubricants, fats, oils, polymers. You can see if there is a mass loss, and then at what temperature there is a mass loss, and you can see how much oxidation takes place. Of course, only if you have oxygen in there. You can investigate the composition of a multi-component system by thermal decomposition. That means if you have a mineral, coal, or whatever, you heat it up under inert atmosphere or controlled atmosphere, you can determine the carbon content, the ash content, the melting point, and the exact decomposition behavior. Of course, you can determine the kind of energy that's stored within the material. You can determine the grade of humidity and the grade of volatiles that's contained in the material, like woods, oils, or in a fat, or the binder content in polymers or whatever. So all this is what's typically done with an STA. Of course, you can use it as a DSC. So what's classic is the melting and boiling point determination, phase transitions, like glass transition, polymorphism of pharmaceuticals, and so on. This is something the DSC does. And what's also of interest is, of course, the influence of reactive atmospheres. For instance, if you have not only oxygen, but hydrogen or other atmospheres, you can see if there's a reaction, so mass loss, mass increase, absorption and desorption, of course. So the thermogravimetric analyzers can do sorption experiments, of course, not only with hydrogen, but also hydrogen. You can do sorption and desorption, create a sorption diagram. You can also measure the heat of sorption if you have a TG-DSC system. And of course, the heat of fusion and reaction enthalpy, which is something DSC does always. In the following slides, I have some examples what typically is measured and how it looks like. After that, I will show you briefly the software and how it's evaluated, and then I'm open for your questions. I see that there are quite a lot of questions already typed in the chat. I will answer all of these after the webinar. So regarding the applications, as I told you, I want to show you some applications that are typically done with the STA, and I'm starting with this rubber decomposition. So what you see here is the decomposition behavior of a rubber sample. This is over time, so the temperature is displayed as this red curve. As you can see, the sample was heated, then there was an isothermal step, it was heated again, another isothermal step, and a third heating cycle. Between the second and the third heating cycle, at that point, the atmosphere has been changed from nitrogen to oxygen. Now I will explain what you can see. The orange curve shows you the mass loss. So during the first heating, there is a decent mass loss, but the green DSC curve does not show any signal. That means there is a mass loss without huge energy release or huge energy consumption. Of course, this mass loss is something that is not really part of your sample or part of the rubber. This is just the humidity that was at the rubber and at the surface. Therefore, the signal of the DSC remains quite flat. So you lose some water, you lose some volatiles here. During this isothermal step, we waited until this effect was over, and then we forwarded with heating. And during the second heating step, there was a quite huge mass loss, and there was a quite clear peak on the DSC signal. So at that point, the sample underwent some pyrolysis, some volatile parts and some organic parts decomposed, some sulfates and nitrates decomposed and were released, maybe even some carbonides were released, and there was a quite decent mass loss. Finally, when this effect was over, so mass was again stable and the DSC signal was baseline again, at that point, the atmosphere was switched from nitrogen to oxygen, and switching to oxygen means now everything that can burn can now burn off. So we went on with heating, and during the third heating here, now with oxygen containing atmosphere, there was a huge exothermic effect. That means a huge energy release because the carbon content now was able to burn off. And this mass loss here shows how much carbon was more or less burning off. So the residual mass, the 40% mass that were now not vanished and still there, must be some inorganics like metals or metal salts or metal oxides. This step here symbolizes the carbon content, this is the pyrolysis content, and this is the volatile content. And if you would integrate this area beyond this peak, you can even get an idea how much energy is released by burning this mass of sample off. And this is how a typical decomposition analysis looks like. Another typical experiment that we always do and we like to do very much for checking the capabilities of the instrument is the calcium oxalate test. Calcium oxalate hydrate is a substance that shows 3 definite mass loss steps with 3 definite enthalpies that can be used to check if the system is working correctly. The substance decomposes in 3 steps. First of all, it gets rid of the water during the first mass loss step. Then the second mass loss step, it loses carbon monoxide, and the third one, it loses carbon dioxide. The green DSC curve shows 3 endothermic effects. If you run this experiment in inert atmosphere, like it was done here, the second effect is endothermic. Calcium oxalate decomposes with the exothermic, so the second peak can be in the other direction if you decompose it in air. Depending if it's air or not, this peak is endothermic or exothermic. And this is very often and very frequently used to show if the instrument is working as it should. In this graphics here, there are also some brown lines, and these brown lines come from a coupled mass spectrometer. This mass spectrometer was monitoring the water, so this is the ion current of water, the ion current of carbon monoxide, and the ion current of carbon dioxide. And it clearly shows you that the first mass loss, the water is showing a significant increase, so water is released here, a little bit water is lost there, but no water anymore. So that means this first mass loss is water. Second mass loss has a huge reaction on the carbon monoxide, just a little bit carbon dioxide. So that means you can be sure the second mass loss here is carbon monoxide that's released, and the third one obviously shows carbon dioxide. So coupling a mass spectrometer can help to identify exactly what's going off and what your sample is really doing here. And something special that I want to show you, you might be aware that DSC always is also able to measure the heat capacity, so the CP signal. In this case, this shows a modulated CP determination. I just want to show you that our STA instruments can do the same experiments like a DSC can do without any restrictions. So it can also measure something the chip DSC we have is frequently doing, and what also can be done with our classical DSC or STA or high temperature DSC. So you measure a sapphire reference, you measure a blank correction, and you measure an unknown sample with the same heating profile, in that case with a modulation. And out of the shift of this amplitude of modulation, you can evaluate the CP of the sapphire, get a calibration with the literature data, and then apply it on the unknown sample. CP determination is not so easy. There are several guidelines available, and I can explain that into detail because our next webinar series will be some special applications. One of them will be how to measure CP with the DSC. Anybody who's interested can have a short guideline how to do that. Yeah, and besides that, as I told you, there are special instruments like these pressure balances, or what we also had is a glove box balance, just to mention that. STA, where the electronics were separated from the measurement compartments. So you could place the balance on the furnace, but nothing more, into a hot cell or a glove box, and then control it from the outside. So it's the same system, but separated into 2 parts for nuclear applications or for toxic applications, toxic environments, when you have to use a glove box anyways. So for these special instruments like inductive heaters, separated electronics, high pressure variants, water vapor variants, I want to show you also 1 or 2 examples. I told you with the pressure balance we can do sorption studies. Doing sorption and desorption can be done or can always be done in 2 ways. Either you do volumetric sorption or you do gravimetric sorption. Our balance does a gravimetric sorption. That means you see the amount of adsorbed or desorbed material by change in weight of the material. A volumetric sorption would mean you have a definite sample volume or sample chamber volume, and out of the change of partial pressure, if you have a known amount of gas, pump it into the sample chamber, and then measure the partial pressure within the sample chamber, out of the pressure and the difference to the amount of gas, you can calculate how much gas was absorbed by the sample. With our systems, only gravimetric absorption is possible. This curve here shows an absorption experiment at a Titan surface. So Titan is a known hydrogen adsorbent, and what was done here was the Titan sample was, or titanium sample was heated to 700 centigrades, and then at 700 centigrades, the chamber was evacuated and hydrogen was filled in. And it was not only filled in, it was filled in under controlled pressure and pressure controllers. So we filled in a certain pressure and waited until the weight change was stable again. We noted the mass where the system stopped, then we increased the pressure. Again, we stopped the experiment when the mass change was stable, and then we did the next pressure and the next pressure and the next pressure. And for each pressure, there was a certain amount of adsorbed hydrogen where the TG signal was stable and not increasing anymore. Doing this at several pressures, up to 5 bar and even higher, you get a curve that looks like this. So at 700 centigrades, the capability of absorbing hydrogen of Titan surface looks like that. That means from 0.5 to 5 bar, there's almost no difference. The saturation is already reached at around 0.5 bar hydrogen pressure. And then this sample was able to absorb 2 to 2.5% of its own weight, hydrogen weight. This is a typical absorption diagram. You can do that at several temperatures. Of course, you can do that not only with hydrogen, but also with other gases, and of course also with different surfaces. But this is how gravimetric absorption looks like. This, just that you know and are aware, this is not only one experiment, this is a couple of experiments. Each data point here means doing an experiment, wait until weight change is stable, do the next step and the next step. So each point here symbolizes one experiment. And last but not least, sometimes you need to couple a mass spectrometer, not only because it's nice to see and identify, but you have to, because otherwise you have no chance to identify what's going on. This curve shows thermal decomposition of a cement that was done with a STA that was coupled with a mass spectrometer. As you see on the yellow mass loss curve, there are a lot of mass loss steps. So here's one, the next one, and the next one, and the next one. So a lot of volatile components or a lot of substances and compounds are removed. And the DSC signal shows you a lot of peaks. You do not even know when one peak ends and the other one starts. If you have samples like this, where you have a lot of effects close to each other or ongoing effects, you cannot identify these effects just by TG and DSC. In that case, you need to further investigate what's going on. And one good method is to couple a mass spectrometer to see which mass units are increasing at what point. Then you can identify, okay, I have water that's released here, here, here. I have carbon monoxide and carbon dioxide at a certain point. And therefore, this helps to interpret your result, quite good and quite well. I'm just showing this to make clear that not everything can be answered by an STA. Even if the combination of TG and DSC offers a lot of possibilities, sometimes you need a third instrument or you need further investigations to identify what exactly is going on. Otherwise, for instance, this mass loss over here could not be identified. If you see the mass trace, you know, okay, it's sulfur dioxide that's left or that's removed over here. But without knowing this from the mass spectrometer, you have no chance to identify effects. Especially if your sample is not known, you have to do something like that, just that you have seen that. I want to thank you for the attention so far. I'm not yet finished. This is just the presentation. I will now show you a short, or give you a short introduction of our software, that you have seen how the STA software looks like and how it operates. So, I'm sorry, it's the wrong window. Sorry. Okay, this is the STA software, how it looks like if you control our instrument. Our STA and in general, the software of our thermal analysis equipment is divided into an evaluation part and a control part. What you see here is the control part, where you do programs, you write temperature segments, you do every setting what the instrument shall do. And the evaluation software can be installed on any other PC. You can access it by network, or you can just copy the results and do the evaluation at home or wherever you like. But beginning with this one, this is the control software. And this is needed at the PC that is connected to the instrument. Otherwise, the instrument won't work. The software looks more complicated than it actually is. On the left side, you see some general settings, like the actual temperature of the sample, the actual temperature of the furnace, the actual status of the instrument. Then you see a selection of sample holders over here. So depending on the sample holder, you can use, as I said, with the STA, you can use TG only sample holders, you can use DSC sample holders, this 3D type sample holders, and different types of thermocouples. If you have more than one furnace, the STA-PT1600 offers you to operate with more than one furnace. You can select which furnace is in use. For instance, you can have a low temperature and high temperature furnace side by side, and then you can use whatever you want to do. These here are the general settings, and in the general settings, it's not really much that you have to type in before you can start an experiment. Of course, you have to fill your sample into the crucible, place the crucible in the instrument, and then do some settings, but it's not really much. First of all, what's really needed is to select the type of crucible material. As I told you, we offer various metals, we offer ceramics, depending on the kind of sample you want to measure. So you have to select what kind of crucibles material you are using. Then you have to type in the name of your sample or of your experiment. And this is something I have to explain. You have to weigh the sample on the lab balance and then put it into the system. Our TGA and also our STA are not able to determine the absolute weight. The problem is that the balance always starts at 0 and then monitors or shows you the mass change. The absolute weight of the measurement system in the sample can be quite huge or can be quite small, and therefore has to be weighed by hand and then typed in here, because the maximum change of mass is 2.5 grams or minus 2.5 grams. If you would exceed that, the system would not be able to measure that. Therefore, you have to type in the weight by hand. The sampling interval should be default at 1 data point per second. You do not need to, but you can write a customer name and also an order number. You can select where you store your data. And you can select what kind of experiment you want to do. In general, there are 3 types: correction measurement, sample measurement, and calibration measurement. In the thermal balance, the DSC as well as the STA, you need to do a correction run before you do a sample run. A correction run means you place 2 empty crucibles in there, do the same experiment like you later do with the sample, because you want to have your background signal and your background noise that has to be subtracted from your experiment later. Therefore, you do a correction run up first, then put the sample in, and then you do the sample run, where the correction run can be selected here and can be automatically subtracted then. As I told you, STA means also DSC. You can also do a calibration measurement. Calibration measurement means you measure a known reference material for calibration of your enthalpy accuracy. So you measure melting metal like indium or like lead, zinc or whatever, a known mass. That means you have the known melting enthalpy, the known melting point, and out of the signal you get, you can create a calibration file that has to be applied on your DSC signal later on. The STA can be used as TG only, as DSC only, or as both at the same time. If you do not need one of these signals, you just can remove this little check here and then do only one of these 2. Or, of course, you can also disable both, and you do not get any signal. But if you want to measure TG only, you can just switch off the DSC, and the same way for DSC only. Or you can do both at the same time. You can type a comment in here, and what we also offer as a special option, you can do event control or event triggered mass loss. So the heating rate is not linear anymore. the heating rate is set by a certain weight loss or a certain peak shape. So at the moment something happens, the software lowers the heating rate, that the weight loss is more or less at a constant rate. This is something special you could do. Once you have done all your settings here, you have to create a temperature profile. Temperature profile means you can define a heating rate and the target temperature, and you can do many segments. For instance, you start with 20 Kelvin per minute up to 1000 degrees, maybe a little dwell time. Then you have a next segment and the next segment. You have the next target temperature, target rate, and so on. You can add infinite amount of segments. That means you can create a profile that's infinitely long and going up, going down, whatever you need. As you see here below, you see a little preview of your program profile. So this is what you're heating, little dwell time, cooling, little dwell time, heating again, and so on, depending what you want to do. Once you have done all these settings here, you just have to tear your system. So as every balance, you have to tear it to 0 before the experiment starts, and then you can basically start the measurement. There's one thing that is special with our STAs. The STA-PT 1600 series comes with an automated inbuilt mass flow control block. That means you have a digital gas control for 3 gases, 1 purge gas and 2 sample gases. And you can program segments now, like you have seen at the temperature side. So the temperature profile is shown up here, and now you can create segments for your gas. For instance, you can define a gas flow. Maybe you want 100 square centimeters per minute, given a little race time that it has a chance to reach that flow. And then it suggests you some dwell times. So it suggests you how long the segment might be. The temperature time points that are selected here or suggested by the software here are the segment ends of your temperature profiles. So if I select this one, the gas flow will end at the first segment ends. Of course, you can edit. Now it's ending at the last segment, and therefore you can adjust your gas profile quite easily to your temperature profile. This is something that always comes up with the STA, and for all the other instruments, it's an accessory that you can buy as an option and you can add. Of course, it also works with manual gas control, but the STA-PT 1600 series has this inbuilt automated gas control. Once all these settings are done, as I said, you have to tear your system, then you can click on Start Measurement and the current values would be displayed. When your measurement is finished, the evaluation of a typical TG DSC or STA curve is also quite easy. This is the evaluation software. As I told you, it's a separate program. You can install on almost any PC. You have to open a project, load a curve. I will now just load any kind of STA curve to show you how it looks like. Let me take this one. So usually you consider mass change and DSC versus temperature. I'm not doing a correction now at the moment. I'm just showing you the curve. So you have a delta M and you have a DSC signal. All you need to do in general is subtract the zero correction. I don't have any at the moment because I would have to find one. I'm just doing this in theory. You have to subtract a zero correction. Usually this would now flatten the curve a bit. And then you can simply transfer this TG signal into the relative mass change signal, as most people are not interested in absolute mass change because the absolute mass change depends on the sample mass you have used. Most people are interested in the relative mass change, so therefore you will have relative mass change in percent. Then you can define, just by right-clicking, you can define the mass change steps at each significant step. System will automatically show you the percentage, and that's all regarding the evaluation you would have to do. For the DSC, it's a little bit more difficult. Of course, you also would have to do a zero correction, which I do not do at the moment. So that's the reason why these effects and these small effects are still there. After zero correction on the DSC signal, you see it's still microvolts. Usually DSC gives you milliwatts or gives you heat flow as an energy. Therefore, you have to apply a calibration. Just imagine you would have been doing the calibration before. You have to apply enthalpy calibration. I just selected any one. Now the signal was transferred into milliwatts. And now you would be able to mark these peaks it doesn't matter if you do not really fit the edge of the peak. Software will automatically, out of the derivation, define where the peak starts and stops. And out of that, the software gives you the onset, the offset, and of course the enthalpy at this peak in joule per gram. And that's all you basically need to do to evaluate such a curve. I know this is just a short course and just a short, rough idea how our software works. But if you have more questions, if you have an instrument, or if you're facing some issues, you can contact us anyways at info@Linseis, or give us a short ring, and then we can talk about this in detail later. So far from my side, that's what I wanted to show you. That's what I wanted to do for today. I hope you all had a little impression how the STA works, how it's used, what it's used for, and what we can do and can offer.